potato problem. At time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh dt equals negative 1/4 times the quantity h minus 27, where h of t is measured in degrees Celsius and h of 0 is 91. One thing you should know, they do not give extraneous information in AP Calculus questions. You will use every bit of information they gave you. A. Write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. Layla, how do you feel about baked potatoes? I love them, she says. A is the classic tangent line problem. Remember, to find a tangent line, all you need is a point and a slope. They gave me the point. I know my point is 0, 91 because I'm wanting to find the tangent at t equals 0. And I need the slope. Well, they gave me the slope right here. So all I have to do is replace the h with 91, and I have my slope at this point. So it's negative 1/4 times 91 minus 27. And that gives me negative 16. Okay, so my tangent line, and you want to label this all clearly. Write the words tangent line. No need to find, I was going to say no need to find the y-intercept. You can just use point slope, but this is the y-intercept. So y equals negative 16 x plus 91. If you want to just do the point slope form, you can always do that also, right? That would just be y minus 91 equals negative 16 times x minus 0. That's the point slope, which is the same as this. So either one is perfectly fine. The next part of this is they want an approximation for the temperature at time 3. So you can say h of 3 because h of 3 is the temperature. Very important, do not say equals. Use the approximately equal to. I'm using my approximation. So it's going to be negative 16 times 3 plus 91. And that gives me 43 degrees Celsius. They did not tell me to use units here, so you don't have to include units. Only include units when they ask you to. And I'm just noticing one thing. They did in the question use t instead of x. They're not going to take off points, but if you can, it's best to use the variables they give you. So I guess I should have used a t. Do not, however, put an h here. You want to put a y there. Because remember, this is the tangent line. This is not the function. We're using this tangent line to approximate this function. B. Use the second derivative of h to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. B is another classic question. It's saying find the second derivative. Again, this is just Leibniz's notation for second derivative. It's nothing algebraic, it's just notation that means second derivative. It's just like this, right? So I want to find the second derivative. Well, there's my first derivative, so I'm going to be taking the derivative of this. You know what I might do first here, just to make life easier, I'm just going to, in my derivative that they gave me. I'm just going to rewrite it first by distributing through. So the second derivative is just going to be the derivative of this, which is going to be negative 1/4. And then you have to realize that h is an h, not a t. That's the dependent variable. That's like the y. So the chain rule applies. Times dh dt. Cannot stress enough, when you take the derivative of something and you have an a dependent variable in there, like your y, the chain rule applies. So don't forget the chain rule when you're taking the second derivative. Now, let's keep going. What is that dh dt? Well, dh dt is this right here. Yeah. It's just the equation they gave me at the beginning, the differential equation they gave me at the beginning. So that's my second derivative. I'm just going to simplify this. A negative 1/4 times a negative 1/4 is a positive 1/16. Here is my second derivative. So we have the second derivative, and now we're going to use that to decide if my answer to A is an overestimate or an underestimate. Remember, second derivative tells me about concavity. If h of t is concave up, and I have a tangent line, then any point on that tangent line that I use to estimate the value will be an underestimate. If, on the other hand, h of t at this moment, when time is 3, is concave down, any tangent line that I have will give me an estimate, a y value estimate, that would be an overestimate. Does this make sense? So I found an estimate at time 3 of 43 degrees. Well, that means I need to know at time 3 is my second derivative positive or negative? Well, there's no place to put in a t, and I don't know what my h is at time equals 3. So I go back to my stem, I go back to the question, and I see in that third line it says the internal temperature of the potato is greater than 27 degrees for all times. So they basically just told me that h is always bigger than 27. So that is their way of telling me this is always going to be positive. I'm multiplying it by a positive. So my second derivative is positive, which means h of t is concave up. So all you would have to do is show all this work and say h of t is concave up at t equals 3, since d squared h over dt squared is positive. And therefore, and so, the estimate in part A is an underestimate. C, for t less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation dg dt equals negative the quantity g minus 27 raised to the 2/3, where g of t is measured in degrees Celsius and g of 0 equals 91. Find an expression for g of t. Based on this model, what is the internal temperature of the potato at time t equals 3? C is a classic separation of variables problem. For some reason they decided to give us a different differential equation, but that's fine. So you have to get all your g's on one side and your t's on the other. I'm going to leave the -1 over there and bring the dt over there just to make things a little easier. I'm going to divide both sides by this whole thing, which, if you think about it, will just give me a g minus 27 to the -2/3 over here on the left. So I just brought the g terms over here, the t terms over there. It does not matter where the negative lives, but it's just easier to keep it over there, I think. I'm going to take the integral of this side with respect to g, the integral of this side with respect to t. This is not too bad. The antiderivative of this is just g minus 27 to the 1/3. There's no chain rule to compensate for, so the only thing I have to compensate for is that exponent. And again, you can just take the derivative of this quickly in your mind to check. Antiderivative of -1 with respect to t is -t, and you have to put the plus c. Don't forget that plus c. All right, now some people like to plug in the x and the y, or the t and the g at this point to solve for c. I don't. I like doing the algebra and isolating g first. It doesn't really matter. There are reasons to do it different ways. Okay, so I just divided by 3. Now I'm going to cube both sides to get rid of that cubed root. So I have g minus 27 equals that whole shebang. And lastly, I'm going to add 27 to both sides. So I have g equals the quantity -t plus c all over 3, all cubed, plus 27. Now I'm going to plug in my, let's see, 91 is my g, 0 is t, and I'm going to solve for that c. Again, I think on the rubric, the College Board plugs in and find c earlier, but this should work. See, I'm going to subtract 27, just doing some algebra here. I've got, let's see, -c cubed over 27 equals whatever that is, 64. And that works out nicely. I get c equals 12. So I just put 12 in for my c, and now I'm looking for the internal temperature of the potato at time 3. So I'm just going to put a 3 in for there. Just plug in a 3. And when you plug in the 3, you should get 54 degrees Celsius. Ba-ba-da-ba-ba.